Welcome to this lecture. This is the first lecture of week 4. In the previous week, we have seen three modes of convergence of random variables, namely convergence in LP, convergence almost surely and convergence in probability. We had reformulated some of these convergences into different terms and we had also compared between these convergences. What we have seen is that the one of these convergences, namely convergence in probability, is implied by the other two, but for all other implications the directions are not true. There are counter examples in all these opposite directions, but in each of these directions with additional conditions we might be able to get the relevant convergences. For example, the dominated convergence theorem, we have seen that with almost sure convergence and with some integrability bound we can get LP convergences. We have relaxed the assumption on from almost sure convergences to convergence in probability, but keeping the integrability condition intact. We have improved upon the DCT type results that it still implies the LP type convergences. So, we had seen all these type of comparison results. Now, it is time to look at many of these important properties of these three types of convergences of random variables. So, without further delay, let us move on and discuss with the lecture notes. Alright. So, we are focusing on these three specific modes, and as always we will continue assuming that all these random variables that we look at are defined on the same probability space. Now, after comparing all these three types of convergences, our interest now is to look at their properties. Now, let us see one of the important properties of these type of convergences. So, just to set up the notation, we are working with this specific probability space denoted by omega f p, and now if I have these random variables x, y and x 1, x 2 so on, these random variables all defined on the same probability space, then there are these implications about uniqueness of the limit of these type of modes of convergences. So, the first type says that I have to fix a number p between 1 and infinity, both 1 and infinity included. Now, if the sequence of random variables x n converge to x in the LP mode of convergence, and again the same sequence converge to y again in the LP mode of convergence, then the p norm of x minus y must be 0 and consequently x and y must agree almost surely. So, this is the first statement. Just to recall, in the LP type of spaces, what we have understood is that there we are comparing two random variables under this equivalence formulation that they are equal almost surely if and only if x minus y has p norm 0. Now, here it is important to note that we have actually been following the identification that if x is equal to y almost surely, then that introduce a equivalence relation which we denoted by tilde earlier on this LP space of random variables. But then what we said was that we will focus on representatives coming from these equivalence classes and we will not be distinguishing between elements of the equivalence class and the equivalence class itself. Alright. So, in that setting, this is the first result, that if a sequence converges to x as well as y in the LP mode of convergence, then x minus y must have p norm 0 and equivalently x and y should be equal almost surely. Now, we can make a similar statement if the convergences are of the form with almost sure convergences. Now, what we are saying is that the same sequence converges to x as well as y, but in the almost sure mode of convergence, then x and y must match almost surely. So, again this is another uniqueness of limit, but here we are considering almost sure mode of convergence. And the third type that we have seen was the convergence in probability, and we make a similar statement that if the same sequence x n converges to x in probability and x n converges to y again in probability, then x and y must match almost surely. So, this statement talks about the three types of convergences and in each case it says that the limit random variable must match almost surely. So, this is the notion of uniqueness of limit that we are using in this context. Alright, so let us see the proof of these results. So, we start with the LP mode of convergence. Here just to recall, we have the norm p being a norm function on this collection of random variables. So, again we are working with p between 1 and infinity, both 1 and infinity included. Now, here there is this simple triangle inequality which we can apply. So, norm of x minus y, p norm of that is less or equal to x minus x n p norm plus y minus x n p norm. So, now this is true for all possible natural numbers n. So, this relation we highlight by star. Now, it is given that x n converges to x in the p norm and it also converges to y in the p norm, and therefore, these two quantities goes to 0 as n goes to infinity. Now, we have these two limits, and going back to this relation star that we have highlighted, what we will have is that if we let n go to infinity in the relation star, then this quantity which is appearing on the left hand side of the inequality star, that must be less or equal to 0. However, this norm function always takes non-negative values, and hence we must have exactly equal to 0 for the norm value, and hence we go back to that identification through the norm functions, and this was discussed earlier in week 1 remark 2 as well as remark 8 part 2. Just to clarify, remark 2 was for the case p in 1 to infinity, infinity excluded, and remark 8 was specifically about p equals to infinity. So, in either case what we end up having is that the p norm of x minus y is 0, and hence x and y must be matching almost surely. So, that is the notion of uniqueness that we have ensured. Similarly, we can do the similar result for the almost sure convergence. What we will do? We follow the definition. Now, we are given that x n converges to x in almost sure mode, as well as in the almost sure mode it also converges to y. So, therefore, as per the definition, there exist two sets A and B with their probability being 0, such that on the complement of the set A, we will have the pointwise convergence to the random variable x, and on the complement of the set B, we will have the convergence to the random variable y, where we have just appealed to the definition of almost sure convergence. But now, what we look at is the union of these two null sets. It is immediate that the probability of the null set is 0. To see this, let us look at the standard subadditivity property of the probability function. So, this must be less or equals to probability of A plus probability of B, which is given to be 0, and since probability is always non-negative, again we end up with this relation. So, the new set n that we think of as A union B, union of two null measure 0 sets, that still a measure 0 set. Now, let us see what happens on the complement of this measure 0 set. Whenever you choose omega from n complement, there the sequence must be converging to pointwise to the random variable x as well as to the random variable y. So, hence what we have identified is that on the set of full measure, which is n complemented, on that set you have x and y must match with full probability, right. So, therefore, we end up having the relation that we wanted to show, that x and y must match almost surely. So, therefore, what we have managed to show is that if you have almost sure convergences and if the same sequence converges to x as well as y, then the limit random variables must be matching almost surely. So, let us see the similar statement, but now for the third type of convergence, which is the convergence in probability. Now, here what we are going to do is to repeat a type of an argument that we have seen earlier in the proof of theorem 1 of week 3. So, just to recall, what we have done there was to extract a subsequence of a convergent in probability sequence, and we have obtained a almost sure convergent subsequence. Now, to construct that specific subsequence, we had used a certain type of an argument. We are going to use a similar argument here. Let us see what we observe first. Again this is a very simple triangle inequality, that if you are looking at mod value of x minus y, that is dominated from above by modulus of x minus x n plus modulus of y minus x n, and this is true for all natural numbers n. Now, if you fix any epsilon positive, this previous triangle inequality implies that the left hand side event must be contained in the right hand side event. To see this, observe that if you have x minus y greater than epsilon, and then if this quantity is being greater than epsilon, then following the triangle inequality, either of these two terms must be greater than epsilon by 2. So, that is the claim. Now, if both these terms were supposedly less than epsilon by 2, then by the triangle inequality we must have had that the left hand side is smaller than epsilon, which is not the case. So, therefore, if you are looking at sample points coming from the left hand side event here, then such a sample point must satisfy the condition that either modulus of x minus x n is greater than epsilon by 2 or y minus x n modulus of that is greater than epsilon by 2. So, at the same time both of these cannot be less than epsilon by 2. So, that will violate the left hand side condition. So, therefore, what we have ended up showing is that for all n, the left hand side event is contained in the union of the right hand side two sets. All right. So, now since the left hand side event is contained in the right hand side union, then if I appeal to probability functions properties, then probability is again subadditive. So, that is what we use here, and this inequality is true again for all natural numbers n. Now, note that we have assumed that x n converges to x in probability as well as to y. Now, if that happens, then for all these arbitrary epsilons, these right hand side quantities that we ended up having, they must go to 0 by definition, and therefore, letting n go to infinity, the left hand side quantity that we have, that must also go to 0. Remember here that the probability is always non negative. So, therefore, we are exactly ending up with a equality, and this equality holds for all epsilon positive. Now, let us see what we can now look at is the event modulus of x minus y being strictly greater than 0. Now, this means that x and y must not be equal. So, that is the interpretation of this event. Now, if that happens, then note that there exists some n for which this also happens. Now, this is now writing the left hand side event as an union over all these sets of this type on the right hand side. Now, this is a standard set theoretic identification, and here what we observe also is that as n increases, then the right hand side sets which are of the form mod x minus y greater than 1 by n, such sets as n increases, these sets also increase. And here what we will do, we will appeal to continuity properties of the underlying probability measure, in particular the continuity from below properties of a probability measure, and hence what will happen is that if we take limits of these probabilities, they must approximate the limit of the left hand side event. Now, for each value of 1 by n, which is a type of epsilon that we can consider, each such case has probability 0, that we have proved, and hence this limit must be 0. Therefore, what we have ended up showing is that the probability where modulus of x minus y is strictly greater than 0, that must be 0, but this probability, as we said, is simply probability of x not equal to y, and that is we have what we have shown to be 0. Therefore, x and y must match with full probability, and hence we have the almost sure equality of the limit random variables even when we are looking at convergence in probability. So, therefore, this result that we have discussed right now tells us that if we have any of these three types of convergences, meaning either the convergence in LP, almost sure convergence, or convergence in probability, in all three types limit is unique in the sense that if the same sequence converges to two different random variables x and y, then the random variable must match almost surely. All right. Now, once we have this, we actually can reveal another type of a proof for this last part, where we have shown the uniqueness of limit for the convergence in probability. So, this is the third part that we are going back to. Now, here you note that in the proof we have used an argument similar to the proof of theorem 1 of week 3. However, just to highlight an important point about the structural properties or the logical conclusion of these kind of arguments, we had actually given two proofs of this earlier result, which is theorem 1 of week 3. The first proof actually used the proposition which we have proved just now, meaning that in the proof of theorem 1 earlier, we have shown by using the fact that if the random variables converge in probability, then the limits must be equal almost surely. Now, what is happening is that we had used that in the first proof of theorem 1. However, we had also seen another proof of theorem 1 by an alternative argument which did not use this proposition. So, if we were to use the theorem 1 earlier in the proof of proposition 1, it will not be a circular argument, because we have an alternative proof of theorem 1 without using proposition 1 part 3. So, therefore, we can also appeal to theorem 1 earlier and try to see if we can get a different proof of proposition 1 part 3 as seen here. Now, this is the alternative proof that we are going to discuss, and this is what is using the theorem 1 of week 3. Now, let us recall what was the theorem 1 of week 3. This tells us that if we have a sequence of random variables converging to another random variable x in probability, then we can extract a further subsequence which converges almost surely to that limit random variable x. So, this was theorem 1 of week 3 that we have seen earlier. We are going to use this result now to give a alternative proof of proposition 1 part 3. Let us see. What we are given is that our sequence of random variables x n converge in probability to the random variable x. Now, we will appeal to that theorem 1 and extract a subsequence which converges to x, but in the almost sure mode. So, let us highlight this as relation star. Now, we go back to the other type of convergence that we are given, that is to the random variable y, again convergence in probability. In particular, if we use this specific subsequence that we have found by theorem 1 earlier, this subsequence is a subsequence of the original sequence which converges in probability, and hence this subsequence also must converge in probability to the random variable y. This is just using the definition of convergence in probability. However, what we can do is that we can focus on the subsequence now, which is converging in probability to the limit random variable y, and think of x n k, the subsequence, as the original sequence, and appeal to theorem 1 once more, theorem 1 from week 3 once more. What we will get? We will get further subsequence of x n k, which we denote by x n k l. So, as L goes to infinity, we will be having a almost sure convergence subsequence which now goes to y. So, let us write this as relation double star. Now, as per the relation star, what we have is that this specific subsequence x n k converges almost surely to the limit random variable x, but it has a further convergence subsequence again converging almost surely to y. So, if we were to concentrate specifically on the furthest subsequence, which is x n k l, this is converging to x as well as y in the almost sure mode of convergence. Now, we will appeal to proposition 1 part 2, where we have shown the uniqueness of limit for convergence almost surely, and therefore, we will get that the limit must be unique and they are equal almost surely. So, therefore, we must have x and y matching almost surely. So, here what we have used is the alternative proof of theorem 1 to avoid a circular argument, and that is how by appealing to these specific subsequential limits, we ended up showing that the limit of convergence in probability must be unique in the sense that they are equal almost surely. Alright. So, now let us move on to another type of properties of convergences. We recall from remark 10 of week 1 that in the metric space setup, what we have is that we have a non-empty set together with a distance function satisfying certain nice properties. Such distance functions we called as a metric. So, if we have a set together with a metric, we will call it a metric space. Now, we will say that certain mode, let us denote it by M, of convergence of random variables is metrizable if there exists such a kind of a distance function which we will call as a metric on the collection of random variables such that the convergence holds in the mode M if and only if the distance between the nth term in the sequence and the limit random variable goes to 0 in this distance function as n goes to infinity, and this should be the equivalent formulation. Therefore, what we are saying is that we should be able to figure out a specific distance function, a metric on the collection of random variables such that in the distance function, if the random variables are getting closer and closer to the random variable x, then it must imply the convergence in the mode M that we are discussing. Conversely, if we start with the convergence in mode M, then we should also have the corresponding distances going to 0. So, the question here is about the existence of such a distance function. So, let us see what type of modes of convergences that we have discussed are supporting such a metric. So, typically in this metric that we are going to use, we will use the identification that the distance between two random variables x and y is equal to 0 if and only if x and y match almost surely. So, this is just following from the previous type of arguments that the uniqueness that we have obtained is in the almost sure uniqueness framework, and note that whatever integration structures that we are going to see, their almost sure equalities translates into equality of integrals. So, measure 0 sets do not really affect our arguments. So, therefore, we will always focus on almost sure equalities between random variables, specifically when we are looking at various such modes of convergences, and we will use this specific type of uniqueness of limits. And with that motivation, whenever we are talking about any kind of distance function between random variables, it is good enough they are equal almost surely if and only if the distance between x and y being 0. So, this is the identification of the metric that we have to figure out. So, we start by looking at convergence in LP. So, again as always we are going to continue with P between 1 and infinity, both 1 and infinity included. The claim is that the convergence in LP spaces is metrizable. In fact, we had already discussed this earlier, but let us just recall that fact. So, in week 1 we pointed out that the norm function that we are using satisfies the properties of a norm function, and therefore, correspondingly we had talked about this kind of a distance function on the LP spaces, meaning if we have two random variables x and y in LP, then we can look at the distance between them through the norm of x minus y, the p norm of x minus y. This gives you a metric on the set LP, and therefore, LP together with this metric forms a metric space. Now, in this metric space setup, the convergence that holds is through this metric. So, that was the notion of convergences that we have seen in LP spaces. So, this was discussed earlier in remark 11 of week 1. Now, note that since we already have a explicit metric that characterizes the convergence in these spaces, therefore, the convergence in LP is metrizable with this very explicit metric coming from the norm. So, therefore, whenever you have a normed linear space, immediately you end up with a metric space, and therefore, you can talk about the convergences here through the norm or equivalently through the corresponding metric. Now, let us see other modes of convergences. So, we move on to convergence in probability, and the claim is that it is also metrizable. Now, here is where we are going to go back to some of our discussion that we had in the previous week. Recall that we had looked at certain equivalent formulations of convergence in probability, and those were via certain specific type of functions which we are going to see now. So, for the convenience of notations, let us call these functions d1, d2 and d3. Here what we are saying is that between two random variables x and y, we will look at d1 of x and y defined by this quantity, that it is the expectation of the bounded random variable modulus of x minus y divided by 1 plus x y. D2 is again of the similar type, where we are looking at expectation of minimum of modulus of x minus y with 1. So, this is again, just to recall, this is the minimum of modulus of x minus y and 1. So, this is always bounded above by 1, and therefore, this is a bounded random variable, and therefore, its expectations exist. So, this is the quantity that we are going to assign to d2 of x y, and finally, we are going to look at this d3, which is through this kind of infimum of certain probabilities, which is of this type, that we are going to look at epsilon positive, such that the probability of modulus of x minus y exceeds epsilon is strictly less than epsilon. So, that is the type of functions that we have discussed in our discussions in the previous week, and what we had actually shown was that these convergences are through these three types of convergences, meaning they are equivalent in this sense. Moreover, what can be shown is that these functions actually satisfies the properties of a metric, and therefore, what we are actually saying is that by this result that we have discussed in the previous week, convergence in probability holds if and only if the distance goes to 0 through metric d1 or through d2 or through d3. So, therefore, whenever you have convergence in probability, then you will have that these quantities go to 0 in the distance d1 or d2 or d3 and vice versa. So, therefore, what we have ended up having is that convergence in probability can be seen through any of these three functions, distance functions d1, d2 or d3, and hence convergence in probability is metrizable. Now, convergence in metric spaces has a very interesting consequence. In particular, let us recall the setup from the real line framework. If we have a sequence in the real line which is converging to a point x in the real line, then it is true that every subsequence has a further convergent subsequence which is convergence to the same limit. However, it is also true that this fact is actually equivalent. So, this is actually an if and only if statement, that if you have a sequence such that every subsequence has a further convergent subsequence going to the same limit x, then the original sequence must converge. So, therefore, this is a kind of a characterization of convergence in the real line, which tells us that convergent sequences can be looked at through convergences of further subsequences going to the same subsequential limit. So, this is essentially talking about the uniqueness of the subsequential limits. Now, what we are going to say is that this proof that we perform for the convergent sequences on the real line can be repeated if you are working in any metric space. So, just repeat the argument replacing the distance function which is the modulus on the real line with the appropriate metric that you have in your metric space. Now, the thing is that as long as you repeat the same argument, you will end up having that convergent sequences in metric spaces can be identified through these convergences through subsequential limits, meaning if every subsequence has a further subsequence which converges to this specific limit x, then the original sequence must converge to that number x. Alright. So, now this is the convergent sequences in metric spaces which we are generalizing from our identifications on the real line, but now we are going to appeal to the fact that convergence in probability is metrizable, and hence we can identify convergent sequences in this mode of convergence, namely convergence in probability through these further convergent subsequences. So, let us write out this specific type of a result now, that since this is metrizable, then any sequence of random variables x n's converging in probability to a remote random variable x in probability, that happens if and only if every subsequence of this original sequence has a further subsequence which converges to x again in the convergence in probability sense. So, therefore, we have this nice equivalent relation of identifying convergent sequences, where the notion of convergence is convergence in probability. Now, let us see an interesting application of this fact, that any almost sure convergence of random variables will imply convergence in probability. We are going back to the comparison between almost sure convergence and convergence in probability. First, almost sure convergence directly implies convergence in probability. On the other hand, if you have a convergence in probability sequence, then we can extract a further subsequence which converges to the limit random variable in the almost sure sense. If we appeal to that result, then what we are actually saying is that this previous identification of convergence in probability that we had can be strengthened to this fact, that every subsequence of the original sequence has a further subsequence which converges now in the almost sure sense to x. To see this, let us start with the previous identification, where every further subsequence was converging to x, but in probability. But we can extract a further convergent subsequence which converges to x, and hence we have the forward direction of this fact. On the opposite direction, if we have that every subsequence has a further convergent subsequence, but in the almost sure sense, then it must also converge in the convergence in probability sense, and therefore, we have the opposite direction by going back to remark 4 part 3 that we have discussed earlier. So, therefore, we now have another kind of identification of convergence in probability, but through almost sure convergent subsequences. But now, we will use this last observation to claim that almost sure convergence actually is not metrizable. So, this is something surprising now, that we have seen these other two modes, the convergence in LP and convergence in probability being metrizable, but now what we are going to show is that almost sure convergence is not metrizable. So, the way we are going to prove it is this: if possible, assume that this is metrizable, but then what we will do? We will appeal to identification of convergent sequences in metric spaces. Now, if it is metrizable, then almost sure convergence will guarantee that every subsequence of this sequence has a further subsequence which converges now in the almost sure sense to x. So, this is just by identifying convergent sequences in metric spaces. But now, what is going to happen is that by our earlier observation, this condition is equivalent to the fact that the original sequence must converge in probability. So, therefore, what we are saying is that if almost sure convergence were to be metrizable, then the equivalence between almost sure convergence and convergence in probability holds. But now, what we have seen earlier is that there are examples which we have discussed in the previous week, that there are sequences which converge in probability, but not almost surely, and therefore, almost sure convergence is strictly stronger than convergence in probability. So, however, what we are saying is that if almost sure convergence were to be metrizable, then almost sure convergence must be equivalent to convergence in probability. So, therefore, we arrive at a contradiction, and therefore, our original assumption that almost sure convergence is metrizable must be incorrect, and hence we get the conclusion that almost sure convergence is not metrizable. Therefore, there does not exist any kind of a metric which characterizes convergence in the almost sure sense. So, in this lecture, what we have seen is that first of all, these three type of convergences have uniqueness of limit through almost sure equalities, and then we had discussed about metrizability properties, and we have seen that convergence in LP and convergence in probability are metrizable. However, almost sure convergence is not. We are going to continue discussing about further properties of this type of three type of convergences in the subsequent lectures. We stop here. Thank you.